Good morning, children. So our next topic is equal sets. So two non-empty sets A and B. Suppose there are two non-empty sets A and B. Then we say that these two sets are equal. Okay, if they have exactly the same elements, and we write A equal to B. Otherwise, the sets are unequal, and we write A not equal to B. And you must remember these 2 points. The elements of a set may be listed in any order. Okay, for example, here we have a set which contains 1 2 3, next 2 comma 1 comma 3, 3 comma 2 comma 1. So though the order of the elements are different in each set, but the sets are not different. Okay, they are equal only. Okay, because this set contains the elements 1 2 3, even this set contains the elements 1 2 3. Okay, so they have the same elements. Okay, exactly the same elements, so they are equal. Okay, it doesn't matter in which order they are written in the set. Next, the repetition of elements in a set has no meaning. Okay, like if I write a set like this 1 comma 2 comma 3, or I write 1 comma 1 comma 2 comma 3 comma 2, so here repetition is meaningless. Okay, so if you ask how many elements are there, so you'll be only counting 1 2 3, so 3 elements are there. Okay, we have to ignore the repetition. Okay, examples: let A equal to set of letters in the word follow. Okay, so how many letters are there in word follow? Okay, so we have to write in set A, and set B is set of all letters in the word wolf. Okay, so show that the set A and B are equal. So here for set A we have got this. Okay, F comma L comma O comma W, and for B we have got W O L F. Okay, here you can see though the orders, okay, in which the letters are written in both the sets are different, but they have exactly the same elements. Yes, so these two sets are equal. Clearly A and B have exactly same elements, so therefore A is equal to B. Show that phi and this set, singleton set, and this is 0, okay, are all different. So here phi is a set containing no element at all, so phi means an empty set. Here this is a singleton set, contains one element, that is 0, and 0 is a number, not a set. Okay, so hence these three are different. Okay, next comes equivalent sets. Two finite sets A and B are said to be equivalent if they have same number of elements. Okay, so not equal sets are always equivalent, but equivalent sets need not be equal. Why equal sets are equivalent? Because equal sets have exactly same element, so obviously number wise also they are same. Okay, so two sets, finite sets A and B are said to be equivalent if they have equal number of elements. Okay, for example, here set A 1 3 5 and set B 2 4 6. Okay, so these two sets are equivalent because set A has 3 elements, set B has 3 elements. Okay, but they are not equal. Okay, so A and B are equivalent. Clearly A is not equal to B, thus A and B are equivalent but not equal. Now next is subsets. Subset, or set A is said to be a subset of set B. Okay, so if you have a set A and you have another set B, then we would say that set A is subset of B if every element of A is also an element of B, and we write this way: A is subset of B. Okay, this is read as A is subset of B. It means all the elements of A, okay, are contained in B. Then superset. If A is subset of B, then B is called a superset of A, and we write B is superset of A. Proper subset. If A is subset of B and A is not equal to B. Okay, so here A is subset of B means every element of A, okay, is contained in B. So A is subset of B and A is not equal to B, then A is called a proper subset of B, and we write A is proper subset of B. So here that equal sign is removed. Okay, so when we write A is subset of B, so it may happen that A is equal to B. Okay, but when we write A is this proper subset of B, it means that A is not equal to B. Okay, here let us see a set A. It contains three elements 2, 3, 5, and set B contains 2, 3, 5, 7, 9. So here you can say that each element of set A is contained in B. Okay, so in that case A is subset of B. Okay, and you can also see that A is not equal to B. Okay, so you can say that A is proper subset of B. Then every element of A is an element of B, but A is not equal to B, therefore A is proper subset of B. Okay, next let A equal to this. So set A contains 1, 2, B contains 2, 3, 5. Here you can see that 1 belongs to A, okay, while 1 does not belong to B. So here you can see that not every element of A is contained in B. Only 2 is contained in B, but 1 is not contained in B. So therefore A is not a subset of B. Okay, therefore A is not a subset of B. You should remember this. Natural number is contained in whole set of whole numbers. So natural number is subset of whole number. Okay, whole number, set of whole numbers is contained in set of all integers. So whole number is subset of set of integers. Set of integer is a subset of set of rational numbers, and set of rational numbers is a subset of real numbers. Okay, next note, every set is a subset of itself. Okay, example, A equal to 1, 2, 3. Okay, so A is contained in itself, so A is subset of A, so we write A is subset of A. And next, empty set is a subset of all set. Okay, so you always remember that empty set is always a subset, okay, of all set. So here we have got set A, B. So 5 empty set is subset of A as well as B also. So empty set is subset of every set. Okay, and a set is self subset of itself. Next is, if you have got something like this, A is subset of B and B is subset of C. So in that case, A will be subset of C. Okay, that means if A is contained in B and B is contained in C, so A will be contained in C. Okay, next, for any two sets A and B, if you have something like this, that A is contained in B and B is contained in A, it implies that A and B are equal. Okay, next is universal set. If there are some sets under consideration, okay, so suppose we have got few sets, okay, that we are dealing with, and we get one set, okay, which contains all those sets, okay, which we are dealing with, then that particular set is called universal set. So here, if there are some sets under consideration, then there happens to be a set which is a superset of each one of the given sets. Such a set is known as universal set for those sets, and we shall denote the universal set by capital letter U or this, okay, this symbol. So let us see example. So we are taking a set A which contains 1, 2, 3, another set B which contains 2, 3, 4, 5, okay, and C is 6 and 7. Okay, now what we'll do is we will take one set which will be superset of all these three sets. Okay, so if we consider the set U, as this 1 2 3 4 5 6 7. So here we observe that this set U is superset of all this set. I mean to say that A is contained in U, even B is contained in C, even C is contained in C. Okay, so A is subset of U, B is subset of U, C is subset of U. So therefore this set is universal set for these three sets. Okay, then clearly use U is a superset of each of the given sets, hence U is the universal set for these three sets. Okay, next is intervals as subsets of real numbers. Let a comma b belong to set of real numbers such that a is less than b. So we are taking two real numbers a and b, and a is less than b. Then we define a closed interval. Okay, so this is called closed interval if we write something like this. Okay, in this rectangle bracket a comma b. Okay, so this means that this is a set of all real numbers, okay, which are lying between a and b. Okay, and even a and b are included in this set. Okay, open interval is written as this. Okay, a comma b with round bracket, or sometimes we write like this. Okay, and this is a set of all real numbers lying between a and b. Here a and b are excluded, so open interval means this, the boundary points are excluded. Okay, so a and b are excluded, but in closed interval a and b are included. Right half open interval. Okay, so on the right it is open. Okay, and on left it is closed. So closed means a is included in the set and b is excluded from the set. So this is a set, okay, which contains all real numbers lying between a and b, and a is included and b is excluded. Left half open interval, that means on left it is open, on right it is closed. Okay, so this will contain all real numbers lying between a and b, where a is excluded and b is included. Okay, if you try to understand this on real line, so you can visualize it like this. Okay, so close interval a comma b on real line, so that means from a to b and a and b are included. Okay, so all the real numbers lying between a and b, okay, including a and b. Open interval means this, all real numbers lying between a and b. Here a and b are excluded. Here a comma b, it is open on right. Okay, so this means all real numbers lying between a and b, okay, a is included, b is excluded. Okay, same goes for this, open at left, so a comma b, this all real numbers lying between a and b, where a is excluded, b is included. You can see examples over here. Okay, so closed interval 2 comma 3, it means it is a set of all real numbers from 2 to 3. Okay, here open interval 2 comma 3 means all real numbers between 2 and 3, but 2 and 3 are excluded over here. Okay, you can check these two also. Okay, next is power set. So the set of all subsets of a given set A is called the power set of A. Okay, denoted by PA, and if number of elements in set A is equal to m, then number of elements in that power set will be 2 to the power m. Okay, so power set is a set which will suppose we are talking about a power set of set A, then it will be set of all subsets of set A. Okay, so let us see example. Write down all possible subsets of A. Okay, here A contains one element, that is 4. So we have to write down all possible subsets of this set. So all possible subsets of A are, so firstly we know that empty set is subset of every set. So phi is subset of A. Secondly, we know that every set is a subset of itself. Okay, so A is also a subset of this here. So here we have got phi and only this set to be subsets of this A. So here power set will be written as this. Okay, power set is nothing but set of all subsets of A over here. Okay, so we'll write phi comma this. Okay, so here you can see that this set has only one element. Okay, so number of subsets, or you can say number of elements in the power set, is given as this 2 to the power 1. Okay, next is write down all possible subsets of this set A. This has two elements, 2 comma 3. So firstly, phi empty set is a subset of A. Next, I can have this as a subset of A. This 3 singleton set is a subset of A, and this 2 comma 3 is subset of A. Okay, so here power set contains these elements. Here I have missed out the curly bracket. Okay, the starting curly bracket I have missed out. So when you're copying it, please write it. Okay, and here you can see that it has got 4 elements, and since number of elements in set A was 2, so number of elements in the power set will be 2 to the power 2. That means 4. That's why we got 4 over here. Next, write down all possible subsets of set this. So here this set contains 2 elements. First element is this, second element is this. Okay, here A contains 2 elements, namely this and this. So let us denote this element by B. Okay, then we'll get set A as this 1 comma B. So it has got 2 elements. Now we have to write down the subset of this set A. So subset of this set will be phi and itself, and there will be one singleton with 1, one singleton with B, and that is all. So here subset is collection of subset, or you can say power set will be this. Okay, and in next step you just replace B, okay, by this. So this is the all possible subsets of set A. Write down all possible subsets of phi. Okay, so phi has no element, that means 0 element. So this will have 2 to the power 0, that means only one subset, and that is itself. Phi has only one subset, namely phi. So power set of phi will be this. Next is operations on sets, union of sets. So the union of two sets A and B denoted by this A union B. This is read as A union B. Okay, is the set of all those elements which are either in A or in B or in both A and B. Okay, mathematically we write like this: A union B is equal to set of all elements which are either in A or B. Okay, so suppose an element lies in the union of A and B, it means that that element is either in A or B. Okay, here this double implication means if and only if. Okay, example, here we have taken a set A which contains 3, 4, 5, 6, set B which contains the elements 4, 6, 8, 10. We have to find the union of this. So union of this, in this you have to write all the elements of A and B, okay, without repetition. Okay, so in this A union B you have to include all the elements of A and B without any repetition. So firstly you can see that 3 is in A but not in B, still you have to write here. Okay, 4 is in A as well as in B, so you write only once over here. Okay, you won't write 2 times. Next, 5 is in A but not in B, so fine, we'll write here 5. 6 is in A as well as in B, but we'll write only once over here. Then 8 is there and 10 is there. Okay, that means A union B is nothing but you have to write each and every element of A and B, okay, without repetition. Done. So you're including all the elements of A and B, putting them together. That is union. Let A equal to x such that x is a prime number less than 10. So this is a set of prime numbers less than 10. Okay. Set B is set of natural numbers which are factor of 8. So firstly what we'll do, we will write this A and B in roster form. Okay, so A is 2 3 5 7. Okay, all the natural prime numbers less than 10, and this set B in roster form will be this 1 2 4 8. These are the factors of 8. Now we have to do the union. Okay, so that in that means that you have to write each and every element of A and B without any repetition. Okay, so you get this A union B 1 2 3 4 5 7 8. Okay, so this is all for the second lecture.